Hi folks, Astronomy Live here. In a couple of my recent videos, I addressed this claimed asteroid threat that was supposed to hit Earth last weekend, and as expected, nothing happened. However, on Monday, a bright meteor was seen near Gladstone, Australia, and they're now claiming that this is somehow related to the asteroid threat, which they say has been delayed. The actual main asteroid has been delayed until October by nuclear strikes that were launched against it. Now, in one of my previous videos, we took a look at the various payloads that were actually being put into space by the rockets that were said to be secretly a part of this asteroid diversion attempt. And so, the claim was that these rockets were secretly launching nukes to try to divert an asteroid, but I showed you guys the various payloads in space, and even a video of one of these payloads being put into geostationary orbit. So we saw that, and it's quite incompatible with the claim that these rockets are secretly launching nukes towards an asteroid, and we're going to get into that in this video a bit, as well as address the claim that an asteroid could be delayed by days or even weeks due to a nuclear strike. So here's the video of this meteor filmed from Australia, and you can see there's a guy playing a guitar here under a covering. And we're going to use this as reference to try to determine approximately the minimum altitude of the meteor over the horizon. So as he's playing his guitar, you can see a bright meteor streaks down and is visible there in the sky. Let me back that up one more time. See, it comes down and very quickly it flashes and then sort of fades out. So it looks like it has some sort of airburst event right there. So we can use this image to make an educated guess about the distance of the meteor from the observer. And let's address the claim that this is somehow confirmation about this past weekend's claimed asteroid strike, and that this was actually that asteroid strike occurring. It just happened so far away off the coast that it didn't really affect anyone. So let's try to give a generous estimate for how far away this meteor really was. Assuming this person is about 5 feet tall in his stooped over stance, and assuming he's about 20 feet away, we can also use the top of this covering as the horizon. And this is a very generous assumption because the true horizon is probably much lower in the image. But taking this as a generous assumption, we can use these numbers to come up with an angular distance of the meteor above the horizon of at least 28.6 degrees. So we can use that figure to estimate the distance of the meteor from the observer, but we first need to know what the altitude of the meteor was at this moment when it was undergoing this airburst event. And you can see in this table here, there's an inverse correlation between the size of an impactor and the altitude of an airburst. But let's make another generous assumption here. Let's assume that this meteor was structurally weakened by some sort of nuclear blast before it hit, and so it underwent an airburst event at a much higher than expected altitude. In fact, let's more than double the highest altitude listed on this chart, and let's assume that for whatever reason it underwent an airburst at 100 kilometers altitude. If that's the case, and if we assume that its trajectory was coming down at about a 45-degree angle, we come up with a distance for the impact point of about 276 kilometers. So let's take a look at the situation in Google Earth. Here's Gladstone, and here's an impact point about 276 kilometers out, straight out into shallow water. And I'm deliberately keeping the angle such that it does go into shallow water to minimize any potential tidal wave from a given impactor size. Now, just how big would the impactor be? Well, in the original claim from Little Pebble, he said that it was detected at 2 astronomical units out. Our asteroid surveys generally find asteroids by around magnitude 21 or so at best, and at 2 astronomical units distance from Earth, that translates to an absolute magnitude of about 16.6 if we assume that it was at opposition and that the asteroid's phase was basically full. That corresponds to a physical size of anywhere between about 1.6 kilometers to 2.8 kilometers. That's huge, but let's assume for the purposes of this video that it's at the lower end of that scale and that it's only about a 1.6 kilometer impactor. Let's also assume that its density is quite low. about 1,500 kilograms per cubic meter. Asteroids can be much more dense, particularly if they're iron asteroids. But given these inputs, you still have major damage occurring to Gladstone and even other cities. So what happens? Well, when the impact occurs, you instantly get a fireball, which is over 7 times larger than the Sun, as seen from the observer, and over 7 times as bright. The result? First-degree burns to anyone exposed to that fireball. And it doesn't stop there. About 55 seconds after impact, Gladstone would be rocked by a 7.8 magnitude earthquake. And it only gets better from there. About 14 minutes after impact, the shock wave arrives, with enough power to blow out glass windows and knock down about 30% of the trees in the area. And then, for the grand finale, about 1.2 hours after impact, a tidal wave arrives with a height between 46 feet and about 91 to 92 feet. So basically, the fireball shows up, gives everyone first-degree burns, then an air blast arrives and blows out the windows and knocks down the trees, and then finally the whole mess is covered in water and Gladstone would be hit with a tidal wave. Obviously, that didn't happen, and in fact, if you plug in these inputs but change the distance out to about 500 kilometers, you still have glass windows being blown out, even that far away. And so that means that for points as far north as about Mackay, and points as far south as about Brisbane, you have glass windows being knocked out and obvious damage occurring, not to mention whatever remains of tidal waves hitting and everything else. So obviously that didn't happen. But some are going to claim that, well, the asteroid was knocked off course by a nuke, but this was just a fragment of it, and it's been delayed and won't arrive for a few more days. In fact, that is the claim that Little Pebble is making, that the main core of the asteroid is still intact, it's just delayed, and it will still arrive sometime early this month. So let's take a look at what that would actually require. So in one of my previous videos on this subject, we took a look at the payloads that were put into orbit by the missions that immediately preceded the launch of Osiris-Rex. Those were originally claimed to be attempts to deflect this asteroid. But what we saw is that the payloads of those rockets can all be accounted for in Earth orbit, and that's quite incompatible with the claim that they were launching nukes towards an asteroid. Now, Little Pebble's excuse for this is that they were actually launching decoys, and those satellites are just decoys to fool you into thinking that they were only going to Earth orbit, but secretly the upper stage of the rocket then delivered its nuclear payload to an asteroid. So let's take a look at this in greater detail, and here are the geostationary transfer orbits for each of the 4 launches that preceded the launch of Osiris-Rex and were claimed to be attempts to deflect this asteroid. And you can see that for the most part they're not co-aligned except for Enroll 61 and MUOS 5, which are headed to approximately similar locations on the geostationary belt. Now, not only are the longitudes of the other 2 satellites different, but their angular tilt relative to the ecliptic is also different. The orbital planes are quite different. So if we take a side view, and you can see the side view is aligned to the orbital plane of Enroll 37, you can see that GSSAP is in a completely different orbital plane relative to the ecliptic. Keep in mind, geostationary satellites have 0 inclination relative to the celestial equator, not the ecliptic. Earth's axis is tilted relative to the ecliptic, and so satellites that are orbiting along Earth's equator are tilted relative to the ecliptic. So what does this mean for the claim that they were secretly launching these rockets towards an asteroid in deep space? Well, the easiest way to do that, if you wanted to put up some sort of decoy, would be to have the upper stage of the rocket deliver a payload to a geostationary transfer orbit like this, a very elliptical orbit with its apogee at about geostationary distance, but its perigee still close to Earth, and then use the upper stage of the rocket to conduct another burn when close to Earth and take maximum advantage of the Oberth effect to extend this orbit even further until its eccentricity exceeds 1 and basically it breaks free of Earth's gravity and goes deep into space to intercept an asteroid. The problem is that if these launches were all supposed to be intercepting some asteroid, they should all be co-aligned so that they all head to the same target. But that's not what we're seeing. In fact, it doesn't even appear that these could be somehow different in order to lead a target as it moves over time or anything like that. The order makes no sense. The first launch was NROL 37. Then you had these two, NROL 61 and MUOS 5, and then the last one was GSSAP. So it doesn't even make chronological sense. The only thing that you could do at this point is to somehow secretly use the upper stage of the rocket to circularize the orbit of the decoy, and then conduct the burn from geostationary distance so that all 4 of your rockets can all leave Earth heading off in the same direction to reach the asteroid target. There are, of course, a couple problems with that approach. First of all, you're not taking advantage of the Oberth effect, so it's going to be more expensive in terms of the delta V budget. It's going to require more fuel to do it. And of course, you're also going to be at geostationary distance when you're doing this, so there's a very, very good chance you're going to get caught. Furthermore, you might notice that the orbit of NROL 61 here, the upper stage, brings it into Earth. The orbit actually goes below Earth's surface, and this is not an illusion. This isn't just the limb of the Earth hiding the orbit beneath it. No, it actually goes into Earth's surface, and that's not a mistake. This upper stage was observed by an amateur astronomer who tracked it over time and plotted the orbit, and sure enough, it was already in a disposal orbit. The upper stage of the rocket had deorbited itself so that it wouldn't collect into space as space junk. So indeed, it did deorbit. It didn't go hunt an asteroid after it delivered its payload. It's not a secret mission to go nuke an asteroid. But let's assume for a moment that that didn't happen. It did, but let's assume that it didn't. And let's assume that they were actually secretly launching these things towards an asteroid from geostationary orbit, because again, the geostationary transfer orbits are not aligned such that it would permit them to go after a single target somewhere in deep space. Let's assume that they went to geostationary distance first, and then from there conducted a mission beyond Earth orbit to try to intersect with an asteroid. So with the spreadsheet, I did some calculations here to estimate the vehicle performance of a couple different rockets. The Atlas V in the 411 configuration, this is what launched Osiris-Rex. And also the Delta IV medium in the 4.2 configuration, this is a Delta IV medium with 2 side boosters. This is what launched the GSSAP satellite seen in the previous chart. And so this gets pretty close, but it overestimates vehicle performance a little bit because I'm not accounting for the mass of the payload fairing here. The payload fairing isn't brought all the way to orbit. It's kicked off at some point to increase the performance of the vehicle and increase the delta V budget. But here I'm treating the payload fairing as if it's weightless the whole time. And so it overestimates vehicle performance a little bit, but it does so evenly for both rockets, more or less. So you come out to about 12,000 meters per second total delta V for both these rockets, assuming payload mass equivalent to what their stated maximum mass to geostationary transfer orbit is supposed to be. And so if you take a look at the delta V needed to reach a geostationary transfer orbit without even conducting a plane change maneuver, because remember, geostationary orbits have zero inclination while these rockets are actually launching from Cape Canaveral at about 28 degrees latitude. So the delta V required to reach a geostationary transfer orbit without even conducting a plane change maneuver is about 11,600 meters per second, and this is about what most of these missions require to do that. So we're overestimating here by about 400 meters per second. It might be a little less than that depending on what kind of margin they like to have for these missions. I'm not sure, but we're getting close enough here that we can do some calculations with this and see what the story is, see if it's possible to launch a decoy into a geostationary orbit and then escape geostationary orbit to try to go hunt an asteroid. So that's what you see down here at the bottom. The total delta V required to launch from Earth, escape from geostationary orbit, and intercept a near-Earth asteroid works out to about 15,000 meters per second. It's quite expensive in terms of delta V. So if you don't know, delta V is change in velocity. It basically tells you how much ability a rocket has to move stuff around in space. So let's take a look at some relevant payload masses here. First of all, let's take a look at a paper that was published studying near-Earth asteroid deflection options. So one of the options they looked at was indeed a nuclear strike using the Ares 5. This is a now canceled vehicle. You might notice it looks similar to SLS, and that's for a reason. SLS is basically the successor to the canceled Ares 5. Although Ares 5 was canceled, NASA is now working on the Space Launch System as an alternative. And this was supposed to be a heavy lift vehicle, just like SLS. And back in 2007, before Ares 5 was canceled, they studied its use as a potential option to launch nukes to deflect an asteroid. And the nuclear deflector that they came up with used this B-83 nuclear warhead and had a little rocket engine on there and some sensors to perform terminal guidance. Basically, this whole package right here is just to come in on the last few kilometers and intercept the asteroid for the terminal part of the intercept. And they estimated they could build such a thing for about 1,500 kilograms. And so we can plug that number in here and see what a Delta IV M42 can do with 1,500 kilogram payload mass. You get to a total Delta V budget of about 14,816 meters per second. And again, this is overestimating vehicle performance a bit because we're not even accounting for a payload fairing here, let alone the mass of any kind of decoy. So basically, you're not even going to really make the limit here on the total delta V needed to escape from geostationary orbit. It's the delta V needed to escape Earth's gravity if you start out at geostationary orbit. You really aren't even going to hit this limit. It looks like you are when you look at this number, but you're not accounting here for the payload fairing mass, let alone the decoy mass. So you're really going to be just under this limit. And you're going to be even farther under the limit required to escape Earth's gravity and intercept an asteroid, even a near-Earth asteroid. That's going to require a few hundred meters more of delta V. So even with just a single nuke, you aren't going to be able to get the job done. So basically that's out. The claim that they could use decoys in geostationary orbit and then secretly go intercept this asteroid is bunk. But the one rocket that was launched recently that hasn't been directly observed by amateurs, at least the payload in space hasn't been directly observed by amateurs, was the Atlas V in the 411 configuration. This launched Osiris-Rex, and while many people did attend the launch and saw the launch, including my friend Red's Rhetoric, the payload itself wasn't really easy to observe from Earth because of the trajectory it needed to take. The angular separation between the payload and the sun in the sky was quite low, so we didn't get to see it as it left Earth, unfortunately. However, about a year from now, it's going to swing back by Earth for a gravity assist, and I do plan to observe it at that time. But until then, let's take a look at what this rocket could have done if it had secretly been sent to deliver nuclear missiles to an asteroid instead. If we plug in about 2 B-83 interceptors worth of mass, we come up with a total delta V of about 13,672 meters per second. And keep in mind, this didn't have to go to geostationary orbit. It wasn't supposed to in the first place. It was supposed to escape the Earth-Moon system. And so it doesn't have a need to put a decoy into geostationary orbit first. And so the total delta V needed to directly escape Earth orbit from a low Earth orbit, taking advantage of the Oberth effect, is much less. It's only about 12,520 meters per second to escape Earth orbit, and then to go intersect with a near-Earth object, it requires about 13,320 meters per second. And that'll get you to a near-Earth asteroid. And as you can see, with two B-83 interceptors on board, you would be just over that limit. Once you account for the fact that the payload fairing is going to have some mass to it, you're basically right at that limit. So let's say that they launched two B-83 type nukes to this asteroid using the Atlas V in the 411 configuration. These warheads supposedly have about a 1.2 megaton yield, but let's be really generous here and assume that they can eke out a 1.5 megatons out of it somehow. So we get up to a 3 megaton detonation in total using two of these interceptors. Now, if we come back to that paper, it actually shows how much you're going to be able to change an asteroid's velocity using a 1 megaton detonation for various sizes of asteroids. And notice the chart here uses the same density for the asteroid that we used in our earlier page looking at the impact effects, 1,500 kilograms per cubic meter. But the chart only goes to a 1 kilometer asteroid. They weren't even counting on having to ever deflect a 1.6 kilometer asteroid. That's huge and really, really difficult. But we can use this data to extrapolate out further and see what could be done using 3 megatons and a larger asteroid. And if you do the math on this, taking this data point here at the upper end of the range of performance of about 0.1 meters per second, once you get up to a 1.6 kilometer asteroid, even with a 3 megaton detonation, you're only going to be able to deliver about 0.07 meters per second delta V. That's really, really low. So if we assume very generously that the Osiris-Rex mission was secretly a mission to deliver nukes to an asteroid and throw it off course, even if it impacted the asteroid on the very day it launched, given the time to impact on Earth, it's only going to have moved about 114 kilometers, which is measly and basically nothing. In terms of delaying the impact, 114 kilometers works out to no more than about 10 seconds, even if the asteroid is moving very slow. Even if it's only moving just above Earth's escape velocity and has an orbit very, very similar to Earth, it would still only delay impact by about 10 seconds or so. That's it. It would not delay the asteroid by a day, let alone by a week or later into this coming month of October. So, no, that's not how it works. If you could delay an asteroid's impact by a day, you would completely avert the impact itself because the Earth would no longer be at the intersection point between the asteroid's orbit and the Earth's orbit once the asteroid gets there. Earth moves in its orbit around the Sun about 2.5 million kilometers per day. However, as we've seen here, even a 3 megaton detonation would not significantly delay or move a massive 1.6 kilometer wide asteroid. And so it would still hit Earth, even if you hit it with a 3 megaton nuke weeks before impact. This is why it's very important to find potential impactors long before the impact, because you need to administer that kind of delta V well in advance of any potential impact in order to move the asteroid enough that it doesn't strike Earth. I hope that answers your questions. If you have any more questions, please leave them in the comments section. I'm hoping to do more videos in the very near future about my satellite and asteroid tracking software and update you on my progress with that. Thanks for watching. Please subscribe for more. Clear skies, folks.